Okay, so the last section is the central limit theorem. We started this applet last time, and we did make some observations, and we're just going to repeat this applet and see if we can make the same observations again. So I'm going to pick now a sample size of sample size 35. So we have this population. As you can see, this population is bell-shaped. It's normal. It has a mean of 25 and a standard deviation of 5. What we're going to collect from this population samples of size 35. So each sample has 35 items in it. And we're going to pick thousands of them. So this is 1,000 times. Here is another 1,000, 2,000, 3,000, 4,000, 5, 6,000. Look, you can keep track of it from here, guys. 7,000 samples. I'm going to pick up to 20,000 samples. There you go. Now we did 21,000. Okay. Let's make some observations, guys. These are the samples that we selected. So we selected 21,000 samples. What this applet did, guys, it computed the mean of each sample, and it did a histogram right here of all those sample means. So what you see here, 21,000 pieces of data all put together. I think you guys agree with me that the new shape of the samples, the sample means, is also bell-shaped. It is bell-shaped, as you can see. It looks very symmetric, very much like, just a bell-shaped curve. Now, what else do you notice? The mean of the original population is 25. The mean of the new sample means is also 25. Well, it looks like 24.9968, but if you guys round to the nearest even 3 decimal places or 2 decimal places, you're going to get 25. So it is very much the same. So now look at the standard deviation. The standard deviation of the original population is 5. The standard deviation of the sample means is 0.8531. What I would like you guys to do, just like what we did last time, take this standard deviation 5 and divide it by the square root of the sample size, which is 35, and see if we can come up with 0.8531. Let's do this together. So here's what I like you to do. Take the 5 and divide it by square root. I don't know why the annotation is not working well. Square root of 35. All right, so what do you guys get? I'm gonna do that as well. 5 divided by, why square root of 35, guys? Because the sample size is 35. All right, let's see what we got. Answers here. Okay, 0.85. And if you round this to 2 decimal places, it's going to be 0.85. So in statistics, guys, rather than working with the population itself, it's always better to work with samples, because the samples do represent the population. They give us the same mean, which is the same measure of center of the population. But better than this, they give us a smaller standard deviation. And what I told you last time, guys, it's always to have consistency in the data set. And consistency means a smaller standard deviation. When the data is consistent, that means they have very similar characteristics. There is not much variation. And we try to eliminate variation in data sets, guys. And that's why it's always better to work, just with samples, with sample means instead of the original population, because as you notice, the standard deviation is a lot smaller, but the mean, the center is the same. Let me reset this, guys. And now, instead of this, I'm going to do a skewed right population. There you go. Okay, so the mean is about 20. Let me just see if I can get 23. It's a little bit hard. Yeah, it's hard. The mean is 23.23, and the standard deviation, guys, is 7.8534. Let me just clear the drawings. And we're gonna pick samples of size, let's say 40. And we're gonna draw. So no, now look at the population. It's not normal, it's not bell-shaped. But let's see what's gonna happen with sample means. So we're gonna do thousands of samples of size 40. There is 10,000 samples, guys. You want more? There is more. Let's do 20,000. 20,000 samples. You can see this. Okay, what do you observe, guys? Even if the population is not bell-shaped, it's skewed to the right. It has a mean of 23.23. Do you guys agree with me? If you round the mean of the sample means to the nearest two decimal places, it's going to give you 23.23. Look at it right there. Now I would like you to take the 7 and look, the shape is normal, it's bell-shaped, although the original population is not bell-shaped, but the new population of samples is bell-shaped, that's what we want. Everything, guys, that you studied so far is based on having a population that is bell-shaped. So it's bell-shaped. Take the 7.8534 and divide it, guys, by square root of 40, and let's see what you get. Whether you're going to get 1.2362 or not. So let's do that. So I'd like you to do 7.8534 and divided by square root of 40. And someone give me an answer. Let's see. This is the algebra that I want you. So 1.24, perfect. And if you round 1.236 to two decimal places, it will be 0.24. Isn't that amazing, guys, that we know the answer that's gonna come from the applet, even before the applet does the work, because you already now know the results. You don't need to see it. All right, so clear all drawing. And then we're gonna do one last attempt. I'm gonna change the shape of this population and make it a skewed left population. So reset. And we're gonna do this. See, I can just put data as much as I want. There you go. So the mean is 31.13, and we're gonna select, let me change the sample to anything above 30. So I'm gonna do like 36. That's easy. Square root of 36 is 6, guys. And we're gonna draw thousands of samples. Remember, the mean is 31.13 here. Watch. I wanna do 10,000 samples. Or if you want to do more, we did 11. Let's do 20 since we've been doing 20,000 samples. It's all in the blink of an eye, guys. All right. You notice the original population is not bell-shaped, but the new sampling population of the sample means is bell-shaped. It is narrower, so guys, you agree with me that the standard deviation is smaller. And let's see the mean. What is the mean? 31.13. Look, it's 31.13. Isn't that amazing? And then, and then standard deviation, guys. Take 8.8499 and divide it by square root of 36, which happened to be 6. And I think some of you already put the answers in the chat. So 8.8499 divided by square root of 36. And I got 1.47 if I round it to two decimal places. Look, guys, perfect match. 1.47. Now, last thing, I'm just gonna reset this one and do a bell shape one more time. Okay. We're gonna keep it as normal, and I'm just do a sample size of size. So the original population now is normal. I'm gonna do a sample size of 16, less than 30. You will know why 30 in a second. And number of samples, let's do it 1,000 times. 2,000, 3,000, 4,000, 5,000, 6, 7, 8, 9, 10,000. I'll do 20,000 just like we did before. All right. So notice, guys, if the original population is bell-shaped, the sample size is small, it's only 16, and we drew 20,000 samples. We did 20,000 means. Look, the mean is remaining the same as the mean. 25 is 24.997. If you round it, it would be 25. And then the standard deviation, guys, take 5 and divide it by square root of 16. Square root of 16, guys, is 4, and 5 divided by 4, I think it's easy to do. It's 1.25. Look, guys, a standard deviation. If you round it, it will be 1.25. And look how narrow, just the data and the sample means, and how wide the data and the original population. So always good to work with samples. Now we're just gonna go back and write some conclusions from this. Okay, so let's put some notes together. So it says, watch the simulation demonstrated in class carefully, then write your observation below to complete the central limit theorem. So the central limit theorem. Use mu for the original population and mu of x bar for the mean of the sample means. Remember, guys, we had two graphs. The top one was for the original population and the bottom one was for the sample means. It's telling me use the mean mu, this symbol, for the original population, and use this that symbol for the sample means. And use sigma for the original population as a standard deviation, and sigma of x bar. X bar refers to the samples, guys, for the mean of the sample means. So what is the first observation, guys? The mean of the sample means mu of x bar is equal to what? Who can tell me what's the first conclusion? That's the mean from the bottom graph, and that's the mean from the original graph. What did we notice? That both of them are what?
They're the same.
They're the same. That's the first observation. Very good. And what about the standard deviation of the sample means is equal to the population standard deviation divided by, who can complete this for me? Square root of sample size. And we write it like this, guys. Sigma of x bar will be sigma divided by square root of n. Okay, so you will see how we're going to use this. So you're wondering, what does this mean? You will see that in a few minutes. When the original population is normally distributed, that means it's bell-shaped, then the distribution of the sample means is also bell-shaped. Normal. Remember, the word normal, guys, means bell-shaped, regardless of the sample size. Now, when the original population is not normally distributed, I showed you like couple population where they are skewed to the right, to the left, and we use a sample size more than 30. So when the original population is not normally distributed, then the distribution of the sample means is bell-shaped if we use a sample size which is 30 or more. So in other words, when working with sample means, guys, if your original population is not bell-shaped, you are required to select samples of size 30 or more. If you select samples of less than 30, it would not work. It will only work if the original population is bell-shaped. So watch here, guys. This is a population. It's not bell-shaped. You can see it's an arbitrary population. It's not skewed to the right. It's not skewed to the left. It's just a population. It has a mean and it has a standard deviation. If I pick samples of size 30 or more, look, the original the sample means distribution will be bell-shaped with the mean equals the mean, and the standard deviation will be sigma divided by square root of n. So that's leads to this. Now here, let's take this. It's a normal population. I don't care about the sample size. It could be anything if the original population is bell-shaped. It could be n equals 5, n equals 7, n equals 100. It doesn't matter as when the original population is normal. So that leads to this. And again, you will get mean equals mean, and standard deviation of the sample means is the standard deviation divided by square root of n. Any questions here? Square root of the sample size. That's what I put there. Square root of sample size n. Let me show you some quick application of this here. Example 11. Let's do this. And then we'll do a real probability question, show you how to use this. Seller phone bills for residents of a city have a mean of $63 and a standard deviation of $11. So mean is 63 and standard deviation, guys, is 11. Random sample of 100 cellular phones bills are drawn from this population. So the sample size is 100. N is 100 here. So sample size of 100 cellular phone bills are drawn from this population, and the mean of each sample is determined. What's the mean? And let me tell you what that means also in a second. And the standard error of the mean of the sampling distribution. He wants the mean of the new distribution of the sample means, and he wants the standard deviation of the new distribution of the sample means. They call it a standard error, which is this, guys. So what he's asking you to find is this and that. This is called the mean of the sample means, and this is called the standard deviation of the sample means, or the standard error. So in order to answer this question, you already know the results of the theorem. You say mean of X bar equals the original mean, which is what? $63. And sigma of X bar, guys, which is sigma divided by square root of n, square root of 100. And what is the standard deviation? It's 11. And what's the square root of 100, guys? It's 10. It's $1.1. And that answers the question. You notice, you see the standard deviation of the sample means? It's a lot smaller than the original standard deviation, which is 11. I would prefer to work with a data set that has a variation of 1.1 rather than a data set that have a variation of 11. That's a lot smaller variation than the previous one, than the original one. All right. Exercise 12. And we're gonna go back to exercise 9, which mimic your assignment, guys, in a second. The training heart rates for all 20 years old athletes are normally distributed with the mean of 135 beats per minute and a standard deviation of 18. So mean, guys, is 135 and standard deviation is 18. Random samples of size 4 are drawn. Once he says size 4, put, guys, n equals 4. And the mean of each sample is determined. Find the mean and the standard error of the mean of the sample and distribution. Okay. We need mean of X bar and sigma of X bar. So who can help me and tell me what's the mean of the sample means is going to be?
135.
135 according to the theorem. And I didn't make it up, guys. You watched the applet and you saw the results. And what's sigma of X bar? It will be what? Who can give me the fraction? What would that be?
Is it 18
Divided.
divided by the square root of 4?
Exactly. Which is 18 divided by 2, which is 9. Now notice, guys, the sample size is less than 30. When the sample size is less than 30, we are required to, for the original population to be bell-shaped. And look what he says here. The training heart rates for all 20 years old athletes are normally distributed. So he mentioned that. If he didn't mention that, I could not use the theorem, because when the sample size is less than 30, we are required to have a population that is normal. But I want to show you here in the one that we did before. He says cellular foam bills of residents have a mean and a standard deviation. He didn't mention whether the population is bell-shaped or not. And we don't care. Why? Look at the sample size, guys. It's 100. When the sample size exceeds 30, then we don't care what the shape of the population is. Now you ask me why 30? This is a little bit beyond the scope of the course, but 30 is the cutoff number here. Okay, now we're gonna do a real exercise.
Is there going to be a question like if the sample was under 30, like do we have to change anything?
Let me tell you what question you could use. I'll give you a probability. There are probably one or two. He'll give you a probability question. He doesn't say that the population is normally distributed, and he asks you to find a probability with a sample size of 10. You said I can't do that because the sample size is not more than 30. But once the sample size exceeds 30, you feel free to do any work. But if it is less than 30, he must say that the population is normally distributed. And actually, in most of the problem, when he gives you a smaller sample size, he's going to mention that, just like I did, guys, in exercise 12. Look, I said the population is bell-shaped. Normally distributed means bell-shaped. Okay, look here in 13. He says, furnace repair bills are normally distributed. And now, guys, you don't care about the sample size once he mentioned that. So with a mean of $266 and a standard deviation of 15, if 36 of these repair bills are randomly selected, so what does the 36 stand for, guys?
The sample?
Yeah, Sam, what is the letter? You need to get used to the letter. N, yes, very good. Good job. N is 36. This exercise will summarize section 5.4, guys. Just watch. It's not going to be different from what we did on Monday, but you will see. So if 36 of these repair bills are randomly selected, what's the probability that they have a mean cost between $266 and $268? Okay. Let's see. Let's fill in the blanks using TI-84 calculator. Okay. Who can help me here? So we want it between 266 and 268. What do I put here? In between. How do you write in between, guys? 266. Is that what you did before? But there is one thing that's missing here. That's not right here. Read the question. Find the probability that they have a mean cost. In section 5.1, 5.2, 5.3, we always selected one person at random and we find the probability of this person. And one thing, here we're selecting a sample and we are asked about the probability of the mean. What is the simple for the mean? The simple for the mean, guys, is not x. Can someone tell me what's the simple for the mean? You can say it if you cannot write it, because you have to write the simple. Yes, with the sign on top. So anytime, guys, he asks you what's the probability of the sample mean, don't put x, put x bar. And now you want to know what difference it's going to make. Watch. Okay, how did I teach you the normal CDF? I said you put the lower bound, which is 266, the upper bound, which is 268, the mean, which is 266, and who can tell me what's going to go in there now? Remember, we're not working with the original population. We're working with the sample means. The original population has a standard deviation of sigma. The sample means have a standard deviation of sigma divided by square root of n. So what's going to be the difference between this section and the previous sections? What do you think I'm going to put in there? You can say it. Not n. What's the standard deviation of the sample means? What's the formula? The original standard deviation is 15, but we're not going to put 15 here. Look what we're going to put.
Is that the one where we do the square root of it?
Exactly. That's how it's going to be. 15 over square root of 36. Because you're not doing x, you're not doing one individual here. You're doing a sample means. The central limit theorem tells you when you work with samples, you cannot use the original standard deviation. You must use the original standard deviation and divide it by square root of 36. So that's the only difference between this section, guys, and the previous sections. And let's do this on the calculator. Do we need to compute 15 over 36 beforehand? No, you can do it in the calculator. Watch. So second, distribute, normal CDF, 266, 268. I do encourage the use of the calculator, guys. 266 here. And look, you put 15, you're going to get the wrong answer. You put 15 divided by square root of 36, you're going to get the correct answer. Close parentheses. And look, guys, that's what we have. That's exactly what I show on the screen, on the paper. And now hit enter. 4 decimal places, guys, it will be 0.2881. You're going to get a totally different answer if you put 15 toward the end. So that is the correct answer. In summary, guys, anytime you have a sample and he asks you the probability of sample means, you do the exact same work as you learned last time, but when it comes to step number 4, to argument number 4, you put the standard deviation and divide it by the square root of the sample size. There's another one, guys. Exercise 14. And we'll do a few more also later. A farmer was interested in determining how many grasshoppers were in his field. He knows that the distribution of grasshoppers may not be normally distributed. So he's telling us that his original population of grasshoppers is not normally distributed. So you guys, you can bet if he gives us a sample size in this question, it has to be more than 30 because the original population is not bell-shaped. So he knows that the distribution of grasshoppers may not be normally distributed in his field due to growing conditions. Yeah, different areas, different, conditions. As he drives his tractor down each row, he counts how many grasshoppers he sees flying away. After several rows, he figures the mean number of flights to be 57. So mean is 57. And the standard deviation is 12. What is the probability of the farmer will count 60 or more flights on average in the next 40 rows? The next 40 rows, guys, this is n, sample size. And he says we'll count 60 or more on average. When he says on average, he's talking about, you know, the mean, the sample mean. So who can help me write, you know, just the interpretation of 60 or more here? How would you write this? On average. So in other words, he's asking you what's the probability that the sample mean is more than 60, greater than or equal to 60. So you guys, you put X bar here, and 60 or more is written like this. Normal CDF. Okay, what would be the lower bound, guys? Yes? What's the lower bound if we want to do 60 and up? You can put it in the chat.
Is it 60?
60. What's the upper bound?
-1 million.
No, it's an upper bound.
A million?
A million. The -1 million will be a lower bound when we do less than, always. And then the mean is 57. But look, guys, because he's doing a sample of 40, you cannot use just 12. You have to use 12 divided by, according to the central limit theorem, that we put the statement over square root of 40. And watch. So clear, second, and distribute. Normal CDF. And now I'm going to put some values there. So we got 60 as a lower, a million. Doesn't matter how many zeros you put there, put as many. 57 and 12 divided by square root of 40. Watch me how I do this. This is, you need to learn how to put this ratio, guys, 12 divided by square root of a number. That's important in this section. And here's the formula. And here's the answer. 4 decimal 5, 6, 9. If they ask you to change it to a percent, as a percent will be 5.69%.